Derivative of a function. Given y equals to fx, we can find the derivative by computing the limit of fx plus h minus fx divided by h as h tends to 0. This is called the first principle. F prime x is the gradient of the tangent to the curve y equals to fx. The process of finding f prime x is called differentiation. The notation that is sometimes used to differentiate y equals to fx is dy dx, or y prime, or d dx of fx, or f prime x. Now let us try to do example 1. We need to find f prime x by using the first principle. So by looking at the formula, we need to have fx plus h. So we have here fx is equal to ax squared plus bx plus c. In order to get fx plus h, we need to change all the x to x plus h. So we will have fx plus h is equal to ax plus h squared plus bx plus h plus c. So this is x plus h, and x plus h. So to solve this question, the formula for f prime x is equal to limit of fx plus h minus fx divided by h as h tends to 0. So we have here limit of ax plus h squared plus bx plus h plus c minus with fx. So our fx is ax squared plus bx plus c divided by h as h tends to 0. Our aim here is to cancel h at the denominator. So in order to cancel h, we need to expand the numerator first. Now we need to factorize h at the numerator. Our next step is to cancel h at the denominator. So we substitute h equals to 0. Then we have 2ax plus a0 plus b. So it's equals to 2ax plus b. So this is the derivative of ax squared plus bx plus c. Now we try to look at example b. So we have here fx equals to x squared. To use the formula, we need to have fx plus h. If fx equals to x squared, so fx plus h will be equal to x plus h, the whole thing square. This is x and x. So x plus h, x plus h. F prime x is equal to limit of fx plus h minus fx divided by h as h tends to 0. So we have here limit of h tends to 0 of x plus h squared minus fx is x squared. So here will be x squared divided by h. Remember that our aim is to cancel h at the denominator, so we need to expand the numerator. In order to cancel h at the denominator, we need to factorize h at the numerator. So we cancel h. So our next step is substitute h equals to 0. So we have here 2x plus 0. This is equal to 2x. So by computing the limit, we get f prime x of x squared is 2x. Example C. So our fx here is equal to 1 over 3x plus 5. We have x over here and this is x. So for fx plus h, this will be equal to 1 over 3x plus h plus 5. So this is x plus h and this will be x plus h. F prime x is equal to limit as h tends to 0 of fx plus h minus fx divided by h. This will be equal to limit as h tends to 0 of 1 over 3x plus h plus 5 minus with 1 over 3x plus 5 divided by h. So our aim here is to cancel h at the denominator. So we need to simplify the numerator. We need to expand the numerator first. We can cancel h. So we substitute h equals to 0. Therefore we have this will be equal to negative 3x plus 5 the whole thing square. D, we have here fx is equal to zx. Therefore fx plus h will be equal to z of x plus h. Have here x and x, so x plus h and x plus h. So the formula is f prime x is equal to limit as h tends to 0 of fx plus h minus fx divided by h. So we have here limit as h tends to 0, z of x plus h minus zx divided by h. Our aim is to cancel h at the denominator. Because we have z at the numerator, we need to conjugate our function. To cancel h at denominator, we have to expand the numerator. Then we have limit h tends to 0. So we can cancel h. We substitute h equals to 0. So we have 1 over x plus 0 plus zx. This will be equal to 1 over 2zx. E, fx is equal to 4x squared minus 5x. So fx plus h will be equal to 4x plus h the whole thing square minus with 5 times x plus h. X plus h, x plus h and x plus h. So we have here limit as h tends to 0 of 4x plus h square minus 5x plus h minus with fx. So our fx here is 4x square minus 5x divide by h. Our aim is to cancel h at the denominator. So we need to expand the numerator. So in order to cancel h at the denominator, we need to factorize h at the numerator. So we can cancel h. We substitute h equals to 0. So we have 8x plus 4 times 0 minus 5. This is equal to 8x minus 5. The derivative at a point by using the first principle. We can find the derivative of the function f at the point x equals to a by using limit of f a plus h minus fa divided by h as h tends to 0, or limit of fx minus fa divided by x minus a as x tends to a. Example 2, by using the first principle, we need to find f prime a for each of the following. So we have here fx is equals to x squared plus 3 and a is equals to 3. So by looking at the formula, we need to have fa plus h and fa. Fx is equal to x squared plus 3. We need to find fa plus h. We have here a is equals to 3, therefore fa plus h is equal to f3 plus h. We have here x and this will be x. So if we need to find f3 plus h, this will be 3 plus h squared plus 3. So 3 plus h and 3 plus h over here. What is fa? So fa is equal to f3. So f3 means that we need to substitute 3 in x. Okay. So we try to do this example. Now f prime a is equal to limit as h tends to 0 of f a plus h minus fa divided by h. We have here a is equals to 3, therefore we have f prime 3 is equal to limit as h tends to 0 of f 3 plus h minus f3 divided by h. So f3 plus h is 3 plus h squared plus 3 minus with f3. f3 means that we substitute 3 into the function fx. So we have here 3 squared plus 3. So this is f3. We substitute into x. Divide by h. Remember that our aim is to cancel h at the denominator, so we need to expand the numerator. So in order to cancel h at the denominator, we need to factorize h at the numerator. We can cancel h. So we substitute h equals to 0. So 6 plus 0, this will be equal to 6. We can also try to use the second formula to find f prime a. So we have here f prime 3 is equal to limit as x tends to 3 of fx minus f3 divided by x minus 3. So limit of x approaches 3, fx is x squared plus 3 minus with f3. f3 means that we substitute 3 into fx. So we have here 3 squared plus 3 divided by x minus 3. We expand the numerator. So when we substitute x equals to 3, we have here 0 over 0. So we have to factorize x squared minus 9. We substitute 3. So we have 3 plus 3 is equal to 6. b, fx is equal to 1 over z x plus 1 and a is equals to 8. So I'm going to use the second formula. F prime a is equal to limit x tends to a of fx minus fa divided by x minus a. So we have xa, and xa. Our a is equals to 8, therefore we have f prime 8 is equal to limit as x tends to 8 of fx minus f8 divided by x minus 8. So we have here limit as x tends to 8, fx is equal to 1 over zx plus 1 minus with f8. f8 is equal to 1 over z8 plus 1 divided by x minus 8. So 1 over z8 plus 1 is equal to 1 over 3 because z9 is equals to 3. Next, we need to simplify the numerator. So we have here limit x tends to 8. So we equate the denominator and times with 1 over x minus 8. Now when we substitute x equals to 8, we will end up with 0 over 0. As 8 plus 1 is equals to 9, so z9 is equals to 3, 3 minus 3 is 0. So we need to conjugate. So this is the conjugate. Now we are going to expand the numerator. In order to cancel x minus 8 at the denominator, so we can factorize negative at the numerator. Now we can cancel x minus 8. So we substitute x equals to 8. So we have negative 1 divided by, we have negative 1 over 54. To determine the differentiability of a function at x equals to a. A function f is differentiable at a point x equals to a if the limit of fx minus fa divided by x minus a as x approaches a exists. It means that the limit of fx minus fa divided by x minus a as x approaches a from the left is equal to limit of fx minus fa divided by x minus a as x approaches a from the right. If a function is differentiable at a point, then the function is also continuous at that particular point. However, a function may be continuous at a point but not differentiable. This happens at points when there are corners or vertical tangents, such as in the diagram below. The slopes have different limits from the left and from the right. Hence, f is not differentiable at x equals to a. Example 1. Given a piecewise function, we have to determine whether f is differentiable at x equals to 0. F prime a is equal to limit as x tends to a from the left of fx minus fa divided by x minus a is equal to limit as x approaches a from the right of fx minus fa divided by x minus a. So in order to determine whether f is differentiable or not, we have to look at the limit as x approaches a from the left and the limit as x approaches a from the right. Now we want to determine the differentiability at x equals to 0. So we have 0 here, 0 from the left and 0 from the right. So our a is 0, therefore f prime 0 is equal to limit as x approaches 0 from the left of fx minus f0 divided by x minus 0. So this will be equal to limit as x approaches 0 from the left. So the function for 0 from the left is 2x minus with f0. f0 is 0 divided by x. So we have here limit as x approaches 0 from the left of 2 will be equal to 2. Try to find the limit as x approaches 0 from the right. So we have fx minus f0 divided by x minus 0. So this will be equal to limit as x approaches 0 from the right. The function for fx for 0 from the right is x squared. So we have here x squared minus f0 is 0 divided by x. So we have limit as x approaches 0 from the right is equal to x. We get 0. So now 2 is not equal to 0. So left hand limit is not equal to right hand limit. Therefore, f prime 0 does not exist. Hence, f is not differentiable at x equals to 0. Example 2. Determine whether the function fx equals to modulus of x minus 2 is differentiable at x equals to 2. We need to write the modulus in a piecewise function. To write modulus x minus 2 as a piecewise function, we can use this method. So we'll solve the second column and write the solution in the third column. So we have here x greater than or equals to 2 and x less than 2. Now the modulus of x minus 2 is equal to, we write the first and third column. We want to determine whether the function is differentiable at x equals to 2. So we have 2 over here, and this is 2 from the left and 2 from the right. Now f prime 2 is equal to limit as x approaches 2 from the left of fx minus f2 divided by x minus 2. So we have here limit as x approaches 2 from the left. Fx is negative x minus 2 minus with f2. f2 is equals to 0 divided by x minus 2. So we have here limit as x approaches 2 from the left of negative 1. So this will be equal to negative 1. Now f prime 2 is equal to limit as x approaches 2 from the right, fx minus f2 divided by x minus 2 equal to limit x approaches 2 from the right. The function is positive x minus 2 divided minus f2. f2 is 0 divided by x minus 2. So we have limit as x approaches 2 from the right of 1. So this will be equal to 1. Now negative 1 is not equal to 1. Therefore f prime 2 is not exist. Hence f is not differentiable at x equals to 2. Example 3 show that fx is continuous but not differentiable at x equals to 1. So we have a piecewise function. We need to check the continuity and the differentiability. First, we need to check the continuity. We have three conditions to be checked. So the first condition is whether the function is defined at x equals to 1. So f1 is equal to 1. So substitute 1 square plus 3. So f1 is equals to 4. f1 is defined. The second condition is to check whether the limit exists at x equals to 1. So now we have limit of x approaches 1 from the left of fx is equal to limit as x approaches 1 from the right of fx. Therefore, limit of fx as x approaches 1 exists and the value is 4. For the third condition, we need to check whether the value for f1 is equal to the value for limit exists. So f1 is equal to limit of fx as x approaches 1. So this is 4. So we can conclude that fx is continuous at x equals to 1. Next, we need to check the differentiability. F prime 1 is equal to limit as x approaches 1 from the left of fx minus f1 divided by x minus 1. So limit as x approaches 1 from the left, fx is x squared plus 3 minus with f1 is equals to 4 divided by x minus 1. When we substitute x equals to 1, we have 0 over 0. So we need to factorize the numerator. And we substitute 1 plus 1, this will be equal to 2. Next is f prime 1 is equal to limit as x approaches 1 from the right of fx minus f1 divided by x minus 1. So we have limit as x approaches 1 from the right, fx is x plus 3 minus f1 is equals to 4 divide by x minus 1 and equal to 1. 2 is not equal to 1. Therefore, fx is not differentiable at x equals to 1.